Good afternoon, this is Schweitzer, and we're going to run through some practice examples of equilibrium involving reaction quotient, which is often referred to as where I'm going, or I am, and where I'm going is the k value, and q will eventually become k. And the question is how long. I guess it could be a long time, or it could be milliseconds, but at some point the ratio of product reactants will eventually reach that of okay, so first things first, we have a chemical reaction above, and AB yields C. What is the expression? Kc equals, there's only one product, which is the concentration of C, two reactants, A and B. Now, looking at this picture here, you might say, okay, well, are we product favored or reactant favored? I got one C. Everything else is simply products or reactants. So I'm going to say that looks like we have more products than we do anything else. Alright, what's the K value for this? Bigger or smaller than 1? Well, generally speaking, although you'll see mathematically it's not always guaranteed, so this is being an estimate. 1 is typically the teeter target point, but in this case, we're going to say reactant favor would be smaller than 1. Well, let's give it a try. Each of these guys is 0.1. What's the value of K? Well, look at this guy. I got 1C, so I'm going to put 0.1 on top here. And I have 0.3 because I have 1, 2, 3, and then 0.3 there. Calculate that out, and let's see what our actual K value is for equilibrium concentration. So 0.1, now 0.3 times 0.3 is 0.09. So 0.1 divided by 0.09, and I get a number that's awfully close to 1. And in fact, it's bigger than 1, sadly. But in some cases, like I said, it's not always going to be smaller. It's very close to 1. But in this situation, with concentrations less than 1, mathematically this does not always hold true, but it is still is reactant favored. So be careful of that, or just don't worry about it, just follow the math. Okay, we did that one. And what is the only way to change, if I want to change this equilibrium constant, what's the only way to do it? And that is to change the temperature. Alright. Next problem. Alright, this thing has changed, and we have a new thing, same equation. Okay, so what's the equation? What's the K for this guy? Same temperature. We're looking at 1.11. No units. Each letter represents 0.1. Determine the reaction quotient for this thing. Okay. Well, now I've got, so I've added some things into here, and I got, okay, my Q is the same thing. C is going to be 0.1. And then I have the bottom here, I have two of them is going to be 0.2 for the B, and then 0.4 here, because I have the 4 A's. And then 2 B's and a C. So I just use that to measure my concentration. Do the math. I got the bottom 0.2 times 0.4. Fairly easy to math to do in your head, maybe. 0.08, and then this guy is 0.1. 0.1 divided by 0.08, and I get point equals 1.25. So what we do here in this case says, okay, to answer the question, to determine the reaction quotient, did that, 1.25. Are we at equilibrium? No. We had too much reactant, too much product. Well, K is equal to 1.11. Q is equal to 1.25. So Q is bigger than K. So we have too much numerator, too much product, not enough reactant. So too much. Let's get this thing here. Let's go. Too much reactant. In this case, no. We have too much product. Yes. Given time, all reactions will achieve equilibrium. To achieve equilibrium, this reaction will stay where it is? No. Lose product and gain reactant. Lose reactant, gain product. Again, you can't gain them both or lose them both, so this is a no, this is a yes. This is what's going to happen. This reaction will proceed losing product, gain reactant in order to lower this value until it reaches the 1.1. Mathematically, this is what will describe how it happens in nature. All right. And that is where we'll stop. There are 2 more problems here for you to try on your own. All right. A couple different versions here. Thank you very much. Have a good day.